Okay, we're going to talk about an example of finding a centroid using Green's theorem. Okay, so we're going to find x bar, y bar of this triangle. 0, 0, a 0, and 0, t. And we're going to use these formulas that we derived using Green's theorem. Remember, there's that minus sign because Green's theorem has a minus sign. And the curve C is obviously positively oriented. We always need that to use Green theorem. So the kind of motivation for this thing again is that computers like one-dimensional integrals more than two-dimensional ones. So this is kind of a sweet formula. But let's just we'll do these formulas analytically. So the first thing you do is you break up the curve into 3 curves. And then we'll do it piecewise. So now we're going to parameterize these curves. And that just means write x of t and y of t. So for C1, it looks like y is 0 on that curve. So just choose x equals t. And use the bounds and use the endpoints for the range. So the range here is just x equals 0, and then it ends at x equals a. For C2, it looks like x equals a and y we'll choose as t. And this will range from 0 to b, using those endpoints. For C3, I'll first find the y as a function of x curve, and this will be y equals mx, because it hits the origin, and the slope will be b divided by a, because it hits ab. So therefore, what we do now is we just use t for x. So x equals t, and y will be given by b over a times x, because we have that line. So now you just plug in x equals t, and we're done. So these are our parametric representations for the curve. So now I'm going to take differentials. This is step 1. I think step 2 is to take differentials, because we need to integrate something, right? So dy is 0, and dx is dt for C1. On the other hand, dx is 0 for C2, and dy equals dt for C2. Finally, for dx, we get dt in the case of C3, and dy is b divided by a times dt. So these are the last pieces of information we need to write that integral down. So for the integral of x squared dy, we'll have C1 plus C2 plus C3. So let's plug it in for each case. So for case 1, we know dy is 0. Oh, I'm sorry. We know dy is 0, so that'll just be 0. So for the second case, we know dy is dt. and we know x equals a. So we should just get, oh, and our t limits, I believe they're from 0 to b. So this looks like a squared b. So finally, for our last one, we know x is t, and dy is b divided by a. And our limits are from, oh yeah, I didn't talk about this. So our x range is actually from a to 0 because we're going backwards. And this is an artifact of that positive orientation. So I'm going to write that integral as a to 0 of t squared b divided by a dt. And so you just add a minus sign to make it normal. So we just get negative b divided by a times 1/3 a cubed. So we just get negative 1/3 a squared b. So overall, we just get a squared b minus 1/3 a squared b. So we just get 2/3 a squared b. So therefore, our center of mass is 1 over 2 times the area of this thing. The area is actually quite easy. It's just half the base times the height of our triangle. The base is a, the height is b. Okay, so we get 2/3 a squared b divided by ab. So it looks like 2/3 a. That is our x center of mass. So if we plot that, it's more than halfway, so it's around right. It's around this line, I think. Which doesn't seem incorrect. Because remember, if we had a rectangle, the center of mass would be halfway, and clearly the mass is shifted to the right. So now let's do the y part. And remember, there's that negative sign. There is that negative sign, but we'll just do that at the end. So, to the y integral, I'm again going to split it up. And I'm just going to use all that information that we already dealt with. So y equals 0 to start with, so that was easy. Now, for the second curve, y is t, but remember that dx is 0, so that's also pretty easy. On the other hand, for this last integral, we know that y is b divided by a times t, but x is just dt. And our integral range goes from a to 0. So this last integral just becomes the integral from a to 0 of b over a squared t squared dt. So we end up just getting negative b over a squared 1/3 a cubed. And what I did was I just, of course, switched those limits to make it normal. Okay, so we end up just getting minus b squared over a squared 1/3 a cubed. So we end up just getting negative a b squared over 3. So we conclude that y bar is negative ab squared over 3 divided by negative 2a. Remember that minus sign is in the y. And the area, of course, is just half the base times the height. So we end up just getting b over 3. And this looks okay, because if the halfway point is here, really our center of mass now is in this line. So the claim is that that is the center of mass, and that's also reasonable, because if we had a rectangle, the center of mass would be at the halfway point, but clearly the masses shift downward from there. And that is clearly what happened. We have a third of b, not b over 2. Okay, thanks for watching.